Welcome, everyone. I'm Mark. We're going to talk today about making testing practical at scale and what that really means. Now, some of you might have joined me back in 2016, presented a talk kind of about a very similar idea, but from a very different perspective. So last time I asked you to be kind of in your own shoes, right? A developer, you're working on some change to the code base, and really what you're worried about is, how can I not break things? What does the workflow need to look like to make sure that I have extreme confidence that I'm not about to break my own product, I'm not about to break something that people depend on my stuff, that fundamentally whatever you're doing is correct. And we went through kind of the whole life cycle of a diff at Facebook, and we started with, well, you're on your dev server, right? You've got linters, which are going to point out bugs. You've got post-processing, address sanitizer, stack traces to help you make those bugs more clear, more obvious for folks who aren't at CppCon and using address sanitizer hopefully every day. We go into our diff workflow. We're talking about how we select. We're going to run all the builds and tests that you need to be sure that you're safe. There's a human component. Eventually, you push the code. Suppose that didn't work. You broke something. Fine. We've got continuous runs. These are cron jobs running in the background. They catch whatever mistakes you've got in trunk. They file a task on you to go fix it retroactively. A-OK. And lastly, and we didn't spend much time on this, there's a deployment pipeline where maybe you're doing shadowing of production traffic, maybe you've got end-to-end tests, something more expensive. So last time, the whole idea was, how do you not break things? Here's the whole workflow that's designed to make that happen. Today, we're covering a very similar space, but I'm asking you to do me a favor, which is step in my shoes a little bit. And I want to give you just a little bit of context. I am an imposter, right? I haven't written production C++ in 4 years, and yet here I am. So what am I doing? What happened? Because I left university doing C++. That was what I wanted to do forever. And I show up at Facebook, and I'm asking myself, how can I best contribute to the C++ community at the company? And at the time, for me, for my money, the obvious answer was our continuous integration needed a lot of love. And so I've been working on that ever since, and for all of you lovely people who are actually writing that code. So my goals are very similar to your goals, I expect. Right? We want to help you find all of those bugs, but we also want to help you find those results very quickly. You know, of course, you don't want to spend a lot of time waiting for results. We want to minimize the impact of whatever test flakiness happens to exist in the code base. Because if you've got a large code base, there's going to be some tests that are flaky. And then lastly, and this one's maybe more for me than for you, we got to survive at scale. We have to figure out how to actually provide that experience in a way that's reasonable. And that's where we're going to be focusing today. Now, just to really spell this out, today our goal is get that same high level of bar of safety that we talked about in 2016, but doing way less work in the process. That's what we're going to be doing today. Now, this talk isn't interesting if there's no scale. There is no talk if there's no scale. Right? If you have one project with 100,000 lines of code, or maybe you just have a few kind of smaller projects, you've got hard problems, no doubt, but this is a different beast. So we've got thousands of developers. We've got millions of files in our largest repos. One of our repos contains most of our C++. And we've got developers in offices around the world, right? People are writing code all the time. And the moment it hits trunk, it's not at deployment, but it's on its way. Right? It is on a pathway to being deployed potentially very quickly. So all of that means the problem of not breaking stuff matters, and it's difficult. So going back, our journey, we want to provide a high, rigorous bar of safety, doing a lot less work. That is the scale we're talking about. That is why we're here. How are we going to do it? Well, caching. Thing number one, we're going to be talking about build graph heuristics, and we're going to see that this is kind of a zoomed out version of C++ builds are hard and or slow, right? That classic C++ problem is going to show up here as well. At toward the tail end of this talk, I'm going to go into how you might configure continuous integration and anti-patterns that are going to make it really difficult to actually optimize any of those goals we talked about, either the amount of resources you need, the amount of time it takes for results to come back, the flakiness, things that on the face of it seem like very tempting things you'd want to be able to configure, but that just blow up in your face and are not actually great ideas. Now, you might be wondering, I imagine rightly, at this point in the talk, this guy's just admitted to us he doesn't write C++. Where's the C++ in this talk? Spoiler alert, there's not a single line of code in this talk. So where's the C++? All right, well, I'm going to ask you another favor, which is I want you to be asking that question to yourself the entire way through. I want you to ask yourself, how would this be different if we were instead talking about writing backend services in Python, if we were talking about writing mobile apps, if we were talking about writing a website, right, like Facebook.com? Why would it be different? And it is. And I'm going to spend a whole bunch of time at the end spelling all of that out, doing each of those comparisons, pointing out why what we're talking about today is distinctly a C++ story. So keep that in mind. All right, show of hands. Who here is happy with their build times? Anyone? We got a hand. I figured we'd get a few brave people. I admire your courage. Now, I find it doesn't matter who I talk to, what company, right, wherever they've been, if you're not doing something pretty small, there's a reason I don't see more than like 3 hands in that audience. So this is where we're going to start, right? And we're going to start not with the problem of like you're compiling your one thing on your local machine and the compile time and the link time for that particular build is kind of nasty. That is a problem. But we're zooming out a bit. We're zooming out to now we're the continuous integration folks. We have to run all of the builds, all of the tests, all of the time as you're changing that code base and figure out which things we should even bother building and testing. So this is the C++ build time problem, just way zoomed out. That's what we're going to be doing. All right, now I figured I could tell you about, flags, when to use O3. We could talk about dynamic linking and static linking. We could even go into modules. But I figured I'd be boring all of you with stuff you already know. So we're not going to do that. We're going to zoom out past that compiler, past that linker. Let's talk about build tools, one layer higher. Now at Facebook, we use a build tool called Buck. You don't need to use Buck to benefit from this talk, no worries. And I should mention at this point that I've got kind of experience with 3 different build tools. So if I get some stuff wrong, tell me after. I'm happy to be wrong. I'd actually love that. The things I know about are various kinds of make. I know Buck, and I've used Ninja like 3 times. And I'm actually really curious. Who here uses make in a substantial way at their company today? How about Buck, Bazel, something like that? Cool. How about Ninja? Something else. Who has anything else? Great. Well, welcome to everybody. For our purposes, you might have guessed it, there are 2 interesting things that Buck does. One is caching and one is querying. And we're going to be talking about both. So let's dive in with caching. I like to think that there's kind of a couple interesting levels of caching, and I'm going to kind of abuse that word a little bit for the first level. If you're building a project on your machine, let's say you say build everything there is, and then you change one file. When you go to build, quote unquote, everything again, it's probably not actually going to build everything. It'll build the incremental difference based on what you changed. So maybe you call that caching, maybe you don't, but I like to think at least every build tool has that. Where things may not have another layer of caching is me and my buddy are working on completely different teams, completely different projects, but both of those pound include some really popular library. We've got an open source one called Folly. Tons of people pound include that thing. So if we're both building that thing, let's say we're both in the same revision, why should we ever compile that object file twice? So if you upload the object file to a cache in the background once you're done compiling it, the other person can download it. Downloading is faster than compiling. Same goes with linking. And Buck does this natively. It also does caching in a bunch of other dimensions we won't go into. If you don't have this today, if you don't have that level of caching, look up the open source projects Ccache and distcc, install them. They're easy to throw into a make file system. You will get benefit. I'm curious, are people using those today? Cool. Lots of hands, not enough hands. Go home, install these things. They will make your life better. All right, well, maybe that's review. Let's go one level further. Who doesn't like to be warm? So, how do you get the most out of your cache once you have one? If you actually have caching set up, great. You're going to benefit from it more if you have a revision where everything is populated in that cache. So we have those continuous runs, these cron jobs. They build and test all of the various things. And one of the nice properties is we build and test all of the projects at the same revision at the same time. And so they are cooperating with each other, right? They're not building many copies of Folly. They're saying, oh, we all need Folly. One job will get it done. You download it, and you're in total doing less work because of this. But not only that, instead of having your developers, let's say, go to master in your source control system, you can provide them a binary which says, go to whatever revision was just warmed in the cache. And if you do this, if you have a revision where everything is warm and you get people to actually use that, suppose you're doing a clean build, no changes against trunk, We've got kind of two different mindsets you might be in for flags, linkers, etc. We've got a debugging, iteration mindset. It's got dynamic linking, not a lot of optimization. It's got sanitizers turned on to find bugs. And then there's an optimized mode. And if you do the optimized mode with a clean build, you get a 6x speed improvement. Now, mind you, that could be faster if we wrote more to our cache. We have certain limitations there, but 6x, that's not bad. How about the iteration mindset? Well, that's a faster mindset by far, being the build mode there, and that's 2x faster. I realize that might be boring because you've already built those things. How about if you make an incremental change? You're still looking at a 15% win on your build speed, right? So having a cache, making sure people are at that cache is really nice. And it's nice for you on your development machines. It's also nice for me when you put up your change for code review, because now the CI machines also get that benefit. All right, well, if up until this point we've been saying, all right, you need to do some amount of work, we can reduce some amount of redundancy, great, but fundamentally you need to produce those object files. We're going to change gears a little bit. We're going to talk about what do you even pick to build and test. Right? That's very different. And I'm going to give you this terrible straw man example, a thing that you would never do when you're Facebook, when you have millions of files in your repo that you need to deal with. And so our terrible idea is, whenever anybody puts up any change for code review, build and test everything. Right? Good idea? Great. So bad idea number one is it's going to use a lot of machine computing effort. It's going to end up with you waiting for the slowest thing in the code base. Whatever that happens to be, you're going to be stuck waiting for it. And I think a lot more subtly is you're going to have the worst flakiness you could possibly experience. Why? Let's say you're writing a test. That test has some non-deterministic, spurious failure rate of 1 in 10,000. Does that sound okay to you? 1 in 10,000, right? Maybe you're talking to a database and it's unhappy. Maybe you're writing a file. Maybe it's a perfect unit test. The kernel's sad. Anyone think 1 in 10,000 is a good rate for spurious failures? I, on the face of it, think that seems almost kind of okay. Well, take millions of files. How many of those do you think are files containing tests? How many tests per file do you think there are? Multiply that all out, multiply it by the 1 in 10,000, and you get an integer. So if you're building and testing everything, you're getting the worst of every single one of these dimensions. Okay, fine. This is a bad idea. We knew it going in. But if you wanted to do it, this is how you'd spell it for a couple different build systems. Let's move on. Let's do something slightly more clever. I know what I'm working on. Let's just say build that particular thing. Right? I'm an engineer. I'm on my machine. Certainly, I'm not spending more resources than I need to. I'm not going to run more tests than I need to, so there's not as much flakiness. All of our numbers look a lot nicer. Here's the problem. I've got myself an arbitrary little build graph here. There's a binary B, a library L, a unit test U. And if I change those red files, right, my binary.cpp, my library.cpp, well, OK, I can say buck build those two things or make those two targets, and it'll figure out it needs to compile the B object file, the L object file, and actually the dot in the center there as well. There's a forward arrow going towards it, so you need that to link together your binary. So it'll figure all of that out, right? You told it what to do now, but it's not going to build your unit test. Now, you could say build the unit test too, but then you have to know the unit test exists. And maybe you know it exists because you were directly touching that library, but what if you were touching something else in a foreign part of the code base? You don't know what tests there are. When you're talking about millions of files, you can't expect to actually know the build graph in intimate detail. So we've got ourselves a problem now. We're a lot more resource efficient, but we're no longer correct. Sorry. What did I do? I skipped ahead a bunch of slides somehow. That's what happened. This is the example I meant to be doing. So, same thing we talked about before, there's just not a purple node. Great, let's do better. And my clicker is having some trouble. All right, this is where we're going to leave makefiles behind. So, what we're trying to do now is to say, given whatever files I changed, and in this example I have one, but you could give a list. Tell me all of the build rules, all of those bubbles in my graph that I need to rebuild, that I need to test. And Buck has this thing, Buck query RDEPs. We mentioned querying would show up. RDEP stands for reverse dependencies. The idea is you're going to say, here's what I changed, follow the arrows backwards to see what depends on the code I changed. And that will tell you what you actually need to do. Now, I actually thought, as of 24 hours ago, that makefiles couldn't do this. I was wrong. I wanted to not lie to you people. There's a lovely person, Beta on Stack Overflow, thank you. check out the link if you want the makefile solution to that. So now what we're going to do is we're going to say, OK, are there any arrows going into B? No, fine. Are there any arrows going into L? There's B, that's redundant, but now there's U. We capture that, we're now going to include it, and we build all three of those, which again builds the center dot as well. Now we are at the point where we are maximally correct. We are building and testing only what we need to. We're not leaving anything out. We're not doing more work than we have to. This is a great place to be. OK, well, it was around this point, this was quite a while ago, that we said, you know, we're maximally correct now. Let's try and do better. Let's look at some data. We learned some interesting things. So first thing we learned is about 2/3 of our computational effort was going toward the diff workflow. 1/3 was going toward that continuous run cron job stuff. And I don't know if that matches your intuition. I have hindsight, but I don't know if it would match my intuition either, because those continuous runs, those cron jobs, build and test everything. And when everything is millions of files, that's going to be big. So the fact that that was only 1/3 is kind of striking, that the diff workflows were so represented in there. That's a lot. And there's thousands of engineers, but that's a big number. So we do whatever we do, and we figure out that one category is bigger than another. We go into the bigger category, and we ask, all right, well, why is it so big? And we learned something else, which was an astonishingly small percentage of the diffs was responsible for an astonishingly large percentage of the machine resource utilization. And that looks like this. Right? It looks like somebody changed that center dot. That might be, for example, that open source library I mentioned, Folly. Right? Lots of people at the end of the day depend on that thing. And if you've changed that, then you need to build everything. And so all it takes is one engineer at this conference, who's changing that library to incur all of that resource utilization. And it's worth it. But we can do better. Right? This is a nasty place to be. OK, so we're going to change our goals. Our goal is no longer build and test all of the things that in a theoretical world you need to build and test in order to guarantee correctness. No, we're going to build what we need to get practical correctness, to be safe in practice. And there's a parameter that I left off our buck query here before, right? And that is that number 2, which says, don't go any further than 2 arrows away from what we changed when figuring out what to build and test. And that picture looks like this. So we'll go 1 arrow away from the center, we'll go 2 arrows away, but once we go that far, that's it, we're done, we're going to stop. Now let me tell you the intuition for why we thought distance would be a good heuristic. We thought that distance would be a good heuristic because let's say you want to make sure you're running the tests for Folly, that center node. Which bubble do you think is the tests? I would say it's that node right there at the bottom, kind of down in the center, right? Because all that's going to be doing, the unit test for Folly, is pound including Folly right away. It is 1 distance away in our build graph. Well, what about a library that just really exercises Folly, right? It just really heavily figures out all of the stuff that it needs to do. It exercises that API completely. That's also going to be nearby. It's probably going to directly pound include Folly. And the further away you go in pound include distance, the less likely you are to be testing Folly itself, and the more likely you are to be testing some abstraction over it. And so, fine, if you leave some things off that are at a higher distance, you're not missing much. Well, here's another take on this. Let's say it's fine if you catch an example of every bug, even if you don't catch every example of every bug. What do I mean by that? Let's say you introduce some sort of crash. Well, probably you're going to find that crash in the part that we are building. You may also find it in the part we aren't, but as long as you see that crash, you'll be able to fix it. Now, there's other kinds of bugs where maybe that doesn't work so well, but there's some intuition for why distance feels like it could be a good heuristic. OK, well, if we apply this on a smaller change, did we break everything? Can we just apply this rule universally, or is this a Folly thing? For smaller things, there's no difference whatsoever. It's exactly the same as if we applied no distance limit whatsoever. There's changes that are of moderate size. It affects them moderately, as you might expect. Cool. So in practice, we are building and testing half as much stuff if we roll this out. Half as much. Right? We're not building half the things. We're not testing half the things. Who thinks we just broke everything? Right? I gave you some intuition, but we're building and testing half the stuff we did before. Did we just break the universe? Who thinks so? Great. Well, I'm glad to see some hands, but we didn't. We didn't. And this is where the practical part comes in. We measure the failure rate in trunk. And we have those continuous runs, those cron jobs, they build and test everything. So we know if something is actually breaking in trunk, right? If at diff time you don't build something and then it breaks, it'll show up. You measure that short term, you measure that long term. You know, it fluctuates a bit day to day, but there was no change rolling this out. You can build and test half as much stuff and be just fine. And by the way, the tests work. They do find bugs, right? It's not that. It's we're building the ones that matter. Okay, well, more practically, about once every 2 months, we do have someone who comes along and we correctly find out that, yes, this heuristic meant we didn't build something we should have and it caused a breakage. That does happen. We miss some things. But at that rate, and let's even assume that there's people who don't report it or we don't quite figure it out, whatever you think that number is, it's so small that for 50%, it's worth it. All right, well then there's opt-outs. From day one, we knew this was going to be like a really risky idea on the face of it, because we saw that it was going to not build quite as much stuff. And we built an opt-out. We said, we're going to make sure that there are these things called deferred jobs. If we would have built it normally and now we wouldn't, we'll put it there. We'll give you an opportunity to say, yes, please build this. And we gave them 3 places to do it. We said you can do it when you put up the change for code review. You can push it as you're looking at the thing at code review. Even your reviewer can push the button. And then again, we advertise it right in your face when you go to ship the code. Hey, you didn't run these things. Would you like to? What happened? First of all, people didn't use it. Right? Nobody cared that there was an opt-out, even though we advertised it very heavily. And it would be really bad if they didn't push it and our failure rate bottom line changed. But that didn't happen, right? They didn't use it, and we saw no more failures in trunk. Well, there was a small subset who did use it, and when they pushed it, they didn't detect more bugs. Now, they did in some cases detect more examples of the same bug, and that might matter if, let's say, you're a person working on a library, you're changing the API, you need to detect every single compilation error so that you can make sure your API change is safe. But in many cases, that just doesn't matter. And lastly, if you're one of these people for which it does matter, we actually still save, because you iterate on your change, getting rid of all the bugs. Eventually, you click the button, but you click it one time. We do that expense one time instead of every time you're iterating. And then we actually remember which jobs fail and always rerun them, never defer them after that point that they've initially failed. So if you iterate on that diff in the future, you're not missing anything. You will be certain that you have fixed stuff. So for all practical purposes, we didn't change the failure rate. This is good. There are some cases where this does not work out. Right? So one case is virtual machines. We've got this thing, HHVM. It interprets the language hack, which is, at this point, thankfully, I would say a distant offshoot of PHP. But you might imagine the unit tests, or maybe end-to-end tests is a better word for HHVM, are some PHP code, where you're running it and you're like, is this PHP code actually producing the results it's supposed to? And the code that actually implements that is this massive C++ project that has a rather large build graph all on its own. And there isn't a relationship between the PHP and your pound including the C++ code that implements that. That's just not how those tests work. It's a virtual machine. The code that implements it is all over the place. There's no relationship between distance and the tests. And if you have no relationship between distance and the test, you can't use the heuristic. We turn it off. Now, the other 2 things on the slide here kind of blend together. We have an RPC framework called Thrift, and it generates nodes in our build graph. In some cases, it might even generate long linear chains like a linked list, a single direction linked list. And I think of those as artificially inflating the distances in the build graph. And so if you discount those all to 0, then you again have no problems, but you do have to actually do that discounting. All right, well, at this point, we're building and testing half as much stuff. We got away with it. We're not introducing more bugs. Fine. Now it just takes 2 of these things to be a continuous run in terms of how many resources you're using. This still isn't great, even though it's twice as good. And so we've got another thing you layer on top. Capitalize on that distance. Double down. Why not? Pick the closest 10. And of course, we don't use 2 and 10 in practice. Those are numbers that fit on slides. But if you do it, there's 8 nodes on the graph that are 1 arrow away, and I picked a couple of arbitrary ones that are 2 away. We do this deterministically. And things are looking better still. right? Same distance heuristic intuition for why this should work. And if you do that, then again, on the smaller changes, there's no difference whatsoever. On the moderate ones, you get a moderate change. And this is another 40%. So that's a multiplication. That's 50% times 40%. We are doing 20% of the original work. And yet, that failure rate is within the noise. It did not change. The user complaints do not go up. The use of the opt-outs, people have figured that out. They know how to develop in this world. So let's go back to our goals, right? I've been, kind of really emphasizing the detect all the bugs part, right? Don't mess up as you're scaling. But there's a real win that I think is practical for each one of you, which is as you're getting code review, as you're trying to find out automatically, did I break stuff? It's going to happen way faster. You're no longer stuck building the slowest thing in the code base. And even if you're not working on Folly, and I should mention the building 20% of what we did before is not for Folly diffs, that's for all of them. That's across the board. So if we look at the time between when you submit a change for code review and when the last thing finishes that tells you whether or not you made a mistake is done, P50 through P99 go way down. Particularly that P99, they just fall to something way more reasonable. So this is really nice for the developers. Now on top of that, before we had 1 in 10,000 times the number of tests in the entire repository. Now you're dealing with 20% of that. So the flakiness goes way, way, way down. Moving the needle on flakiness is an incredibly difficult problem. And this is a great way to do it. If you want an easy way to reduce flakiness in your code base, run less stuff. Honestly, there is nothing easier to do on that front than run less stuff. There are other hard things that you can do. If you go back to my 2016 talk, there's actually another fairly nice thing to do. It's called base rev retries. Check that out. But flakiness is an incredibly hard problem. All of this now lets us survive at scale. Now, forgive me, I'm going to spell out things that maybe are kind of obvious, but we're going to hire more engineers. They're going to write more diffs. There's going to be more code in the repository, and the code is going to be more interconnected. All of that scares me. What doesn't is that we now have a constant RDEPS cutoff. We now have a constant closest n cutoff. And that means that our future, fake data here, going over time, number of engineers, number of machines to support them, is going to look a lot more like that bottom line than that scary up and to the right line. Right? It's linear. We can deal with that. The key idea, and you may do this differently, is that we put an upper bound on the cost of a diff. That matters. OK, up until this point, I've been able to share some numbers about how well things have been working. I want to talk to you about something that is an experimental direction. I don't have data for how well it works in C++, but we've tried it on a certain subset of our web tests, and it works wonderfully for that. We are very close to being able to test this in C++, but I wanted to just share the cool idea. And it's this thing called diff batching. So suppose you've got 3 different diffs, 3 different commits, maybe wildly different things that they're working on, but at the end of the day, buck query RDEPS tells us that they have some things in common, right? They both need to build project A or project C, or this could be build nodes, however you want to think about it. What if instead we just rebased these on top of each other? And instead of doing a buck query RDEPS of just commit 1 and the files that were changed in that, you run a buck query RDEPS on the files that were changed across all 3. You're going to figure out, OK, I need to build the same projects, but now there's no more redundancy. And turns out this case, where we save 2 jobs, that's doing 2/3 of the work in this example, is really, really likely. And it's likely because our job success rate, not our percentage of diffs that have a failure on them, but for each individual job, the success rate of a job is upper 90%, right? It is a high 90s%. And that means this case is extremely likely. You're very likely to save work by doing this. Well, let's assume we got into our unhappy case. Something broke, right? People break code. That's the reason we run the builds and tests. So project C is now busted. We're going to look back and we're going to say, OK, well, it would be useless of us to say, hey, engineer, you broke stuff when we combine your changes with 2 other untested changes. That's no fun. So we look back and we say, diff1 could not have broken project C, because our build graph didn't tell us that C was even on its radar. So we'll run a copy then for diff2, diff3, and we figure out it was diff3 that broke it in this particular case. So we're back to doing the original amount of work, but this case is extremely unlikely. And the least happy case, where all of those jobs fail, is significantly more expensive, but it's also really, really unlikely to happen. So this is a kind of cool thing, and part of the reason I'm hesitant to even speculate on numbers is because there's a lot of dimensions to this problem, right? If you stack more diffs together, then if you get in the happy case, you save a lot more work. But on the other hand, each thing you stack on top increases your percentage failure rate. So you're playing with a trade-off there. And if each diff runs more than 2 jobs, then there's also more overlap and you get more benefit. So there's lots of different ways in which this might work out, this might not. One more example of how you can scale the diff workflow problem. The diff workflow problem was easy mode. Continuous runs is where it gets hard. Why? It gets hard because at the diff workflow time, if I don't run something and it breaks, continuous runs have my back. They're going to file a task on you. You're not going to have a great day, but it's not going out to production. In continuous runs, it's not the end of the line, but it's closer to it. And it's much harder to use heuristics to say, don't do work. It's just a much harder thing to do. So this graph scares me. Let's break this down. Let's see if there's anything we can do in one of these. You need to build and test all of your stuff on a regular basis to see what could go wrong. And if we do this, we can break this problem apart. We can see, if you want to run your cron jobs twice as often, then you're going to end up doing twice as much work. You can ask, well, what flags should I use? And I mentioned earlier we had kind of an iteration debugging build mode and an optimized build mode. And it turns out we use both. We want to run the debugging mindset because it has sanitizers, right? And you want to find your bugs before you ship stuff. And yet on the other hand, you got to use static linking at some point to find those bugs, and you also need to deploy your binary, so you need the optimized mode. So fine, you can play with your flags a little bit, but there's work to do. You got to build and test all the things. Nicely, that becomes the warm revision, and the jobs cooperate with each other. You're running the tests, and then there's a deployment pipeline. Maybe you're shadowing production traffic. Maybe you're running expensive things like end-to-end tests. But this is what we're working with here. Where can we find savings? And I've been misleading you. I've been leaving you under the impression that you got to build and test all the things. And you really don't. And the reason why not is because these cron jobs are running at a continuous interval. So all you really need to do is build the delta, the things that changed since the last one. We're no longer just running make blindly like we did in our straw man way back when. We're saying run buck query on all of the files that changed between all of the diffs, between where we are right now and the last continuous run. It's kind of like a really large diff batching stack. And if you do that, you can save 20% of your costs, right? So now you're only doing 80% of everything. That's still really nice. So we've looked at kind of all these different ways to save computing resources, reduce the amount of time that you, the developers, are waiting for various things, whether that's your diff or sending the binary out to production. We've reduced flakiness by like 80%. None of that is possible without strong CI standardized configs. None of it. Let's talk about why. So first off, this is a very good approximation of what our configuration looks like. It really does have basically 2 things in it. One is, tell me what you care about. What do you want me to make sure is built and tested? And 2 is, if it does somehow break in trunk, who do I file a task on to make sure that you're aware of it? That's it. And there's some things that feel like they should be there, right? That feel like they would give you this lovely sense of control, of ownership that would make your life better. But in practice, they kind of have nasty side effects. Thing number 1. Let's say I gave you an option which said, run my continuous runs every n minutes. And you can choose whatever value n you want. So we're in a repository with millions of files. Imagine how many of these configs do you think there are? How many different times do people tell us, this is what I care about, right? Make sure it's built and tested. And that's a big number. So now imagine every one of them telling us, I want mine to run every minute. I want mine to run every hour. I want mine to run once a week. Right? They give us different numbers. Maybe somebody even tells us some weird number like every 19 hours. You could imagine. Somebody would do it. If you're living in that world, there's a bunch of stuff that happens. So for starters, you're triggering these continuous run jobs at different times and different revisions. You're no longer filling that cache at one revision. So they're not cooperating with each other. They each need to build their own folly object file. And the cache is smart. It can, it doesn't have to be the exact revision. If it's, within a few and folly hasn't actually changed, fine, it'll figure that out. It'll reuse it. But if you're using wildly different numbers, then you really are going to be paying a lot more costs. These jobs cannot cooperate with each other. And then you have no more warm revision. You could maybe have a warm revision per project, but then the moment you want to add a dependency on something else, it's cold. And of course, people are making changes to the code base. That's what you're all here to do. So if you let people pick how often their stuff should run, it actually slows things down. Now, let's say you're the, I want to run my thing once a week person, right? And let's assume that's less frequently than most. You might argue, but I'm saving machines. And the thing is, we don't even run your job if it didn't change. We just saw that with continuous runs. We only build your continuous run job if your project was affected. And so we're not wasting machines building your stuff, making sure that it didn't break, telling you that something broke early while it's still OK to revert it. Right? You don't actually win by letting people configure when to run their job. Now, another example of that, and on the face of it, I kind of really love this one because it seems so simple. It would be super easy to explain, to implement, to debug. Everything about it on the face of it, I really, really like. But in practice is less good. And that is, instead of telling us, this is what I care about thrift, you also tell us, build my config if and only if one of these directories has been modified. So let's say you tell me, build the thrift config if and only if someone modifies a file in the thrift directory or the folly directory. Well, now if I change a file in folly, and with Buck, with the build graph, I could prove that thrift never pound includes that file, I'm stuck. I have to build the thrift config. So I'm wasting machines. And on the flip side, let's say there's a library widget, and thrift pound includes widget. And somebody puts up a diff to widget, and it would break thrift. Now I can't build thrift because you told me not to. And so I'm underbuilding. And so if you tell me, here is a concrete rule for when you should build and test my stuff, then you lose out everywhere. You overbuild and you underbuild, and everything is unhappy. But let's go one step further away from this. Let's not talk about, how do we pick when things should run. Let's just talk about having standardized configs in the first place. Right? Most of our jobs, the build and test stuff that gives you results and tells you whether or not everything is working, are standardized. They run more or less the same code. They all figure out what to build. They build it. They run the test. They do that sort of work. But we have other repositories, folks who have been at the company, by folks I mean projects, for less time, let's say, and haven't gotten on standardized infrastructure. And there's a way to just say, hey, continuous integration machines, here's some work, go do this thing I told you to do. And if you look at a repository that has more of those kinds of jobs, the only thing, when we looked, that they had in common was source control operations. Right? If you were going to try and optimize horizontally across this tier and reduce the amount of work, that's it. That's all you had to work with, because they weren't doing the same thing. It is incredibly important to make sure that if you are at scale, if you are running builds, tests, fuzzers, whatever you're doing at scale, that you are doing it consistently, that you don't have customized jobs, at least not very many of them. Because if you have too many of these things, there's nowhere to actually make it better. All right, nothing we did today works if we don't have this standardization. We saw that you wouldn't get the warm revision if you do the continuous run stuff. If you let people select by directory when to build and test your stuff, there's no more build graph optimizations. There's no more 80% savings of diff workflow resources. There's no flakiness wins, nothing. Now, I asked you at the beginning of this talk to think about, why is this a C++ talk? Because there was no C++ code in it. Why are we here? Why is this at CppCon? And I told you we would be looking at Python backend services, we would be looking at mobile apps, we would be looking at large websites like Facebook.com to tease this apart, to figure out why is what we've been talking about really, truly a C++ story. And I think that it is in that compare and contrast that it really comes to life. So let's talk about Python. Facebook has a ton of C++, but we also have no small amount of Python. We've got enough Python to go around. And that means that we can actually compare these things pretty well. So if you look at our Python, we've got some backend services in that. We've got some scripts. We've got a hodgepodge of other stuff. Why is it different? Thing number one, where's the compile? Where's the linking? Right? There's some small amount of stuff you might do before you just run the code, but it just doesn't even compare to the amount of work you're doing in C++. We saw earlier that, actually we didn't see, I stripped that out. About 2/3 of the work that we do in any given one of these jobs is spent building, linking, whatever you want to call it. So for Python, that's not there. You just don't have that cost. It is a very different beast. And then you take a look at your build graph. And the C++ build graph is wildly different from the Python one. Because in Python, you might have a library like Folly where everyone eventually, or actually probably more like directly, needs it. Right? You've got some core things in every language. Everyone's going to use the core things. But what you don't have is as many layers, as many connections. Right? C++, I think it's well understood that it's a language where you have the ability to say, I'm going to build a layer of abstraction on this thing. Somebody's going to build a layer on top of that. Somebody's going to build a layer on top of that. You're going to have libraries upon libraries upon libraries. Python less so, right? At least in our code base. And we've measured this. You can measure how much stuff do you build and test for a change that only affects C++, that only affects Python. And those numbers are wildly different. The Python graph just isn't as connected, even though there are core libraries that all of these things actually need. So the Python story is different because you're not doing a lot of builds in the first place, your caching doesn't matter so much, and your build graph, the distances are already really, really small because that's just how Python is. Well, what about mobile apps, right? And let's talk about iOS, because in iOS, they do compile. So we've got the Facebook app for iOS, you've got WhatsApp, you've got Instagram, you've got all these things, but the list of these things is actually kind of small. When you're talking about our main C++ code base, we're talking a whole mess of different back-end services and other stuff written in C++, a whole lot of stuff. And so if you manage to break one of these, right, because somehow your heuristic failed, well, you've made one team kind of sad that day. But everyone else is fine. In mobile, if you break the compilation of the iOS app, that's affecting way more engineers, right? Forget deploying bugs to production for a moment. We're not going to do that. But if the compile breaks, if some significant test suite breaks, there are more engineers a day that is slowed down. So the mistakes have a higher cost to them. And so we've got a sibling team at work, folks who come from a machine learning background, and they went where the problem was harder. They went to mobile where mistakes are more costly. And they're able to use machine learning to figure out what should we build and test, not just a simple distance heuristic. And there are papers you can Google for these things. They're available. So the problem there is also different. Even though they compile, the stakes are higher simply because there's more people working on it. And even if you exclude that, their build graph just has a very different shape as well. Oh, sorry. Web. Let's talk about web. So we've got a big website, and there's no compilation to speak of at all. Not a lick. There's no builds. There's no build graph. There's no pound includes, no dependencies to follow. And so if you want to figure out what tests to run, you might be stuck, for example, saying, all right, I'm going to run the tests, see what code that covers with code coverage, and remember that to figure out what tests to run in the future. It's a different ball game. And I don't know about you, right? I know that there are blazing fast C++ unit tests out there. There are blazing fast web tests out there. But I feel like you're more likely to end up with a few tests in a C++ code base that try and do something really expensive. They want to spin up lots of stuff. They want to talk to each other. That seems like a C++ side of the equation that I just don't find as much of when I look at our web code base. And so in a code base where compile time is nothing, and so all you're talking about is execution time, that's also potentially way smaller. It is a very different problem space. And for that reason, what we've been talking about today, the need for caching, the benefits of caching, and how to take full advantage of that, the problem of selecting what should you build and test, and being able to even use distance as a heuristic that is meaningful there, that you're able to play heuristic games and make some mistakes very rarely and not have them matter, that is a property of a C++ code base. Now, our journey today was detect all the bugs and do a lot less work in the process. And we did that by using caching, by using build graph heuristics. We saw that none of that actually works if you have bad CI configs. And we wrapped it up by saying, this is a C++ story. This is different from Python, from mobile, from web. I hope you enjoyed the journey. Thank you very much for being here. If anyone has questions, I'll take them at the mic.
Hi, thanks for the talk. I'm Frank Vasquez. My team depends on RocksDB, and so we want to take advantage of the latest features, but we're often scared to upgrade that dependency because it could break our existing databases that are already out there. Do you have any tips on dealing with that?
So just let me see if I got the question right. Is the question that you're using RocksDB, you want to upgrade it, but you're nervous because it's understandably like a database, and that's a very sensitive thing, and you're wondering if there's tips for how to do that. Is that correct?
Yeah.
Okay. You know, I'm just going to start by saying I don't have a perfect answer for you here, but at the end of the day, you need to have some kind of a test. Whether or not that's a unit test or an end-to-end test or shadowing production traffic, something that says, am I going to break this? And then you need to run it. That's kind of all I can say there, right? You also want to have gating so that you can roll it out a bit at a time, hopefully. I don't know if that's possible in the scope of RocksDB, but hopefully it is. And if you're able to roll it out slowly and compare and measure, that would be how I would say to do it. But the truth is that this is not something I'm an expert on, that particular case.
Thanks.
Yeah.
Hi, I'd like to know concerning the warm revision technique. How are the changes actually pushed by every single developer afterwards? Is that pushed like on separate branches that are going to be merged automatically, or are they blindly rebasing and pushing?
Sorry, I missed that because of echo. Is there any way we can reduce the echo a little bit?
I can talk further back.
Let's do that.
So concerning the warm revision technique, in order to make it work, must the single commits be pushed to separate branches and the automated system merges them back, or are we blindly rebasing and pushing?
Got it. So the question was, for the warm revision, what if you have multiple branches? Do you like kind of do it on all the branches and somehow get it all back together? Is that correct? So more or less, we just don't have a lot of branching. People build off of trunk. And so for that reason, we just don't have to solve that problem.
Okay, but then I expect that in order to have a warm branch, every single commit cannot be warm. And so what is the process for skipping a certain amount of commits and then deciding like, oh, we have a warm branch that is new maybe every 10 minutes or every few commits?
So at some periodic interval, we wake up and we build and test all the things at master, and that becomes the warm revision. There's no particular logic to say how many revisions in the future you should go. It's more of a time-based thing.
Okay, thank you.
Yep.
Okay. Can you hear me from this distance? Okay. I was just curious, like you spoke a little bit towards sort of a standardization effort. I guess I'm just wondering, like, I assume you guys must have gotten some good insights on maybe giving like feedback to how to better improve builds, maybe at the project level. So specifically in C++, we have often the case that, you know, like 8-pound include files are out of control, and you know, like if you had like an intelligent way of like carefully detecting those dependencies at the project level, you could like very much improve your build time. I guess I'm just wondering, like as part of your efforts, like if you guys are investing in like any kind of tools you intend to kind of make available perhaps at both your level and also at the individual project level. Yeah, like as part of also like the standardization of giving some information out of those.
Cool. Let me see if I got that again. So I think what you're asking is, some compilation units are really expensive. Do we have tooling to detect that, or other things to kind of figure out this is where the costs are in your builds? And you know, maybe as an extension of that question, would that ever maybe be open sourced or something like that?
Yeah.
Okay. So we do have stuff like this. They're maybe not as mature as one might hope, but we've got a team of folks who are trying to figure out, you know, hey, how can we actually make our build times more manageable than they are today. And they're looking at this. And we have folks who've been able to do this, but basically with no small amount of effort. If we get it to the point where it's, you just run it and it's basically done, then I think we'd be in a better position to start talking about open sourcing. But until that happens, all I can really say is we've got folks looking at it. Yeah.
For the querying and caching facilities of Buck, it depends on the hash key that you have for every target, a function of all of the inputs. Can you talk about how the tool chain comes into play there? So if you have iOS developers, one of them updates their Xcode, they're now pulling things out of the cache that won't work for them. Can you talk a little bit about that?
So I'm not sure I got this one. I'm going to test my comprehension again. Are you saying toolchain is in like maybe you have to build for Windows and for Linux, and how do you deal with that?
Well, more if, so your CI is filling your cache for Buck for your iOS team, right? What if someone upgrades to Xcode 10.3, but your CI is using Xcode 10.2?
Got it.
Pulling things out of the cache that won't work for them.
Okay, so I think I got this. Let's say you've got a version of a compiler and you're upgrading to another compiler, or maybe just some big important third-party library. How do you deal with that? And I think you were asking, how does it affect the cache? Short term, there is an impact on the cache, right? You don't necessarily immediately transition everything all at the same time. And so you might have to recompile certain object files, bearing in mind that you're using two different compilers, and the build tool can actually take that into account. Long term, and just kind of our general strategy is try not to have very many versions of stuff at any given moment. We try very hard to have no more than 2 versions of anything. And that helps the problem a whole lot. And on top of that, it's not like you can mix and match these things. There's like a mess of them over there, and you upgrade them all at once, and now you're on the next one. And that helps keep the cache from sharding too much.
Thank you.
Yeah.
Hi, I was wondering, a lot of the examples you gave were about library level dependencies. One of the nice things about C++ that we all love is that it's a systems language. So it has much higher incidence of things like garbage collectors, databases, code generation, executables, things like that. Did you find that the depth of reverse dependency still held for those types of things? Or were you mostly just looking at library level dependencies?
I'm honestly having a lot of trouble with just the microphone. I'm going to just jump down here, and let's just talk.
All right. Yeah, so my concern was like the examples you gave were about library level dependencies. Like you're talking about Folly being a very low level.
Yeah.
But something we love about C++ is that you can build the binaries that you use to like in your CI system, compilers, runtimes, VMs, etc.
Yeah.
Did you find that the property of building a small number of reverse dependencies away still held for those?
Yes.
Okay, so
Yeah, so we found that using the distance heuristic held for basically the entire repository. Anything that was not on that slide, it works for. It was the virtual machines, it was the generated nodes that gave us any amount of trouble. Everything else, with whatever distance threshold we were using, didn't blow up as far as we're aware.
You did like take things like block out of the equation and put them as like a given that's already a stable baseline or something like that.
Right. Yeah.
Thanks.
Hello.
Hey, Peter, thanks a lot for the talk. I have a question more about, because this most seems like it's kind of a monorepo that you have, and then I'm working there as one revision.
Yes.
So what would be the suggestion, like if we have like one repo that's kind of a server, one is in C++, let's say,
Right.
another repo that could be like a library that's also in C++ that calls the server, and then another one is, for example, your iOS app that uses that C++ library underneath. So
Yeah.
how to test this like together?
Yeah. Honestly, that sounds just like a wildly different ecosystem. So I would have a really hard time making assertions about the right way to do that. I would go back to first principles and want to measure. In a world where you have different repos for things, I think it's more likely that you would have a stable version of each of those repos. And when you go and depend on another repo, you'd be talking to the stable one, or the directly over the network to a service that's published that you know works. And so with that in mind, the need for, let's say, a warm revision is diminished because most people are building the same thing anyway, right? You get warm for free because you have a stable version of every single library, every single repo that you might depend on. So the trade-off space is just very different. And you also have, less ability to, let's say, use something like buck querying to figure out what should you build, just because it's a less important problem. You've built everything, and then you've got object files that you're maybe, or .a files or whatever it is that you've got directly that you're using. It'd be really difficult for me to hazard a guess.
Okay, so it's like better to have it like optimize it in those one spots and then have like nicer one like build or something and then depend between each other?
All I can say is that that might be the way to do it. I don't want to make an assertion without having tried something.
Yeah, thanks a lot.
Yeah.
Hey Mark, thanks for your talk.
Cheers.
Question about how do you handle a situation with two branches? Let's say there are two branches of master.
Yes.
And they both have been tested independently with respect to the master, and they're both ready to go, right?
Yes.
Now it's like a race, like who gets to merge first.
Got it.
My branch gets merged in. Will this other branch also get merged in without testing with the newest master, or you wait for this branch to be merged again? Because
Yes.
there's a problem with the throughput here, because
So
it takes like 10 minutes for you to do incremental build, you cannot do more than 24 hours by 10.
So even if you wait to run all of your tests until the last possible second before you push the code, there's a race condition, right? Just fundamentally, somebody's shipped some code in that window. And so it's really difficult to avoid this. Today, it's just not that big of a problem in our C++ code base for the same reason why the stakes were higher in mobile, where if the app breaks, a lot more folks care, whereas there's less individual engineers working on each individual backend service. And so the odds of a race conditioning happening there are lower. And so it just hasn't been a huge concern yet. An idea that we've been talking about for if we, and when the day comes where this is a bigger problem, is instead of letting everyone willy-nilly push to the code base, get a whole bunch of folks, right? Grab everyone who's ready to ship in this 15-minute interval and ship them all together and just serialize the stuff. Ship 100 things at a time, you can test them all together, and you can be certain that you're not going to break stuff. It has different characteristics because you're going to be incurring kind of a forced wait time on people, and maybe you'll even be spending more machines depending on when you choose to run your tests. But if race conditions are a big deal, that would be the avenue I would be looking at because you can actually guarantee it that way.
So in the current situation, you don't rebuild with the latest master if individually they have been successful?
We play some games to minimize race conditions, but the emphasis is on minimize, not remove.
Thank you.
Yeah.
How do you define a distance of dependency?
The number of pound includes it takes to get from one bubble in our graph to some other bubble in the graph.
Right, but if you have folly and everyone depends on that, then that distance is all one.
Indeed. And so folly does have an enormous number of things that are distance one. But it also has a bunch of things that are higher distances away because it needs to go through a few other libraries before finally somebody pound includes folly. And so, that's why for folly, we weren't done yet when we just did the RDEPs with a limit of 2 in the slides. We then needed to layer on top the take the closest n. And if you do that, then you're again saying, here's an upper bound. I know folly has a lot of stuff that depends on it directly, but in practice, you can get away with that. It works out.
In terms of the diff batching, if there are lots of people submitting pull requests,
Yes.
then how do you determine how many diff you are going to batch?
So the question is, how many should we choose to batch? And I don't know the answer yet, because like I said, it's in production for a certain subset of our web tests, but for C++, we have not fully rolled this out. We have not tuned the parameters, and so I can't really tell you what the numbers will be until we try it out and see what happens. Yep.
Considering that batching experiment, are you experimenting with heuristics regarding the failure rate of different projects so that you can actually adjust based on the observations?
So it's a lot easier to maintain consistent rules than ones that are different. But certainly we are measuring failure rates and identifying common patterns and doing our best to make sure that whatever those patterns are removed. Cool. Thank you everyone for being here, and if you want, I'll be around for some more minutes.